So since we have understood LSTMs and RNNs and multiple types of RNNs, let's go and actually solve a real world problem using LSTM. This problem has a data set from IMDB. IMDB is basically a website that is owned by Amazon, where you have lots of information about movies. For example, one of the information that you have is you have the review text provided by users and the review rating, right? So the data set that we will use today is you will have review text and whether the review is positive or negative. This is the sentiment of the review itself, right? So what we have here, our XIs, is basically a sequence of words, right? And our YI is a binary classification, 0 or 1. Right? This is the data set we have. Thankfully, this IMDB dataset is readily available in Keras. So what we'll do here is, of course, we'll build an LSTM model, LSTM inspired model on IMDB dataset using Keras. And the reason we chose the IMDB dataset is because it's readily available in Keras. Okay, a very important note that I wanted to mention is LSTMs are very, very tricky, to get them to work. Right? There are lots of little hacks that you have to do to get your LSTMs to work, and there are many reasons why they may not work. Okay, we'll see some of the examples. So what I'll do here is I'll walk through this code that I have very slowly, explaining each of the nitty-gritty details. Because what happens, because in my own professional experience, when I first learned LSTMs, it took me a couple of weeks. It took me a couple of weeks and lot of reading to understand how they internally work and what is exactly happening step by step, right? So I will actually walk you through this case in lot of detail. So it might take a little more time than our regular code examples, but it's important because only by understanding nitty-gritty details would you understand how to actually get LSTMs to work, right? So let's go to our code, right? I'll share the reference link to this notebook, and this notebook is running on Google Collaboratory, right? So you can easily get this code and run it in your own collab.research.google.com website. Okay, so let's go step by step. Before we go, this whole example is inspired from a very nice blog written at machinelearningmastery.com. Right? This blog is actually this page or this blog, Machine Learning Mastery, is a very good blog. I have learned a lot by going through some of these articles, and this is an example that I've taken here, which is sequence classification with LSTM recurrent neural networks in Python with Keras. And the good thing with Machine Learning Mastery has a lot of examples both in Keras and TensorFlow, and their explanation is terrific. I mean, very nicely explained. So I've taken the code from here and I'll explain it to you step by step, right? With more details than you would typically get in this blog. But I strongly recommend you read this blog also. That's why I've provided the credits link here. So after you finish this, I recommend you spend some time reading the blog also, so that if I've missed something, you'll get more clarity. Okay, your standard importing stuff. There are a couple of things. We are importing the dataset IMDB here, right? We are importing the LSTM module here, and there are a couple of other things. We are importing something called as embedding and sequence. We'll see how and why all these things are important as we go and construct the whole thing. So the dataset that is available in Keras inbuilt, because we are importing from Keras.datasets, we are importing IMDB, right? So let's understand how this dataset is internally. So the exact reference for this dataset, you can find it here, right? This is the URL. And if you go here, it explains very nicely on how Keras provides this data. So let me explain how this IMDB dataset is available in Keras. So what they've done, the way they've provided the data is as follows. They've taken all the reviews. They have 50K reviews, if I'm not wrong. They have 50K reviews, and these reviews are broken up into train and test data, right? You can get training data of 25K and test data of 25. You can split it the way you want. Each review, let's call it X1, right? Each review is basically a sequence of words, right? Your review 1 is basically a sequence of words, right? So on and so forth. And you have the Y1 corresponding to it, which is binary. Similarly, your X2, right, is a sequence of words here, X2, 3, so on and so forth, and you have your Y2. And the way, and each of these, remember, each of these is a word. Each of these is a word. And the way they have encoded these words is very interesting. So what they've done is, they first built a corpus. So they've built a vocabulary. Let's call this set V. Of all the words, it's a set of, so they first built a set of all the words. It's a set of all the words. It's a set of all the words in all the reviews, right? In all the reviews. So first they built a vocabulary, and then they said for each word, so let's assume I have a word the, okay? So for each word, they compute the frequency of the word, which means how many times does it occur. So they have word, comma, frequency. They built a table like this, right? For each word that is available in the in this vocabulary, for every word they compute the frequency. Probably the occurs 49,000 times, right? A occurs 50,000 times, so on and so forth. Then they sort. First step is they compute the frequency. Second step is they sort. They sort by frequency. That's the second step, right? So what do you get now? You get basically a table where you have words here and frequency here. So you have word 1 with, let's say, frequency of 50K. You have word 2 with a frequency of, let's say, 49K. This is in descending order of frequency. Now, given this word, let's assume this word is the, and this word is a, and there is another word an, so on and so forth. So for every word, so this is the first word, right? When you sort it, after sorting in my third step. So first I got the frequency counts. Second, I sorted it. Third, I will give the word the an index of 1 or rank of 1. So whenever I see the word the, I'll replace it with 1. Whenever I see a word a, I'll replace it with 2. Whenever I see a word an, I'll replace it with 3. So on and so forth. So whenever I see a review now, x1, right? The way I represent my x1 is basically through a sequence of numbers, right? My x1 now will look like this. My first value will be some word. Let's assume the review starts. So the review actually is the phone is very good, right? Then I'll see what is the rank of the in this sorted list. It is 1, so I'll put 1. Then I'll see what is the rank of the word phone. Let's assume phone is here at some rank, let's say 162. Okay, I'll place 162 here, and so on and so forth. So I've gone from a sequence of words to a sequence of indices. Okay, these are indexes or indices, right? This one basically says that the first word in my sequence is the most frequent word in the total data set. That's how they have it, right? So let's go and see the data for ourselves. Okay, so what I'm doing here is, in this step, I'm saying, so I'm loading my data, and here I'm saying, instead of using all the words, because there may be many words here, I'm saying that I will only take the top 5,000 words by frequency. Okay, so I have a variable called top words with a value of 5,000. And when I say load data, again, if you want the documentation for load data, you can get all of the documentation here, right? So here, what I'm literally saying here is, I want every review to be represented. I want every review to be represented with these numbers. But let's assume suppose I have a word here which has an index of, let's say, 5010. I'll simply skip it, because I said I want each of my reviews to be represented using only the first 5,000 words. If there is a word which is at a rank of 5001 also, I want to simply discard those words. Okay, number one. So when you look at, so I'm creating my training data and my test data here. Now let's look at the training data and how it actually looks like. Let's look at one data point. So if you print xtrain1, what you get is basically a list. So the type of it is list, and it has a size of 189. So there are 189 words here in your x1. Okay, so let me write it down. Your x1 consists of x11, x12, so on, x1, 189. And each of these are numbers. The first number here is 1, right? Which means I have a word here whose frequency, whose rank in my sorted list is 1, right? My second is 194. So I'll have 194 here. So this is the word which in the sorted list here is at 194th position, right? And if I have any word, if you look at this, because we have truncated it and said we only want to use the top 5000 words by frequency, you'll never see an index value here of greater than 5000, right? And its length, this length is 189. Very, very simple. Next comes the very interesting step. This is called padding stage. Okay. So padding, literally what it does is this. I'll explain you why we need padding in a little while, but let's understand what padding does. Now I have my x1, which is of size 189, right? I want to convert each of my, let's say I have my x2, which is, let's say, x21, x22, so on, x2, let's say 200. Let's say you might have x3, which is of x31, x32, so on and so forth, x3 150. So each of these reviews are of different length. This review has 189 words, this review has 200 words, this review has only 150 words. Now we'll apply an operation called padding, and what padding does is as follows. Okay, so let's look at the code. I'll explain you what it does in a little while. So I'm saying that I want the maximum length of each review to be at most 600, no more than 600. Then I'll say both for xtrain and xtest, pad it using the maximum length equals to 600. So what it literally does is, look at x1, right? So what it does literally is, let's take our x1, right? Our x1 has only 189 words, and I'm saying perform a padding with max length equals to 600. What it literally does is, it takes this x1, it converts this x1 into a sequence of 600 words, not just 189 words. Converts into 600 words, right? But it does something called as pre-padding, which means it keeps it inserts zeros before, right? And then it inserts x11, x12, so on and so forth, x1 189, so that this whole length becomes 600. Right? So if you look at the output of x1, so if I print x1 train 1 after padding, the way it looks is this. So look at this. I have 194, 1153 here. Look at these numbers. After I have pre-padded them, I have lots of zeros here. I have lots of zeros, and then my 194, 1153 such, so on and so forth. And its size is equals to 600. So I'm converting each of my sequences. So through padding, what am I doing? I'm converting each of my sequences, each of my reviews or sequences of same length equals to 600. Now imagine if I have a review that has a length of more than 600, I'll simply truncate. I'll just use the first 600 words in it. I'll discard the later words. Okay. Now your obvious question is, why pad? Why are we doing this padding operation? Because if you look at it, theoretically speaking, right, our LSTMs, from the theory that we learned, one of the key things about our LSTMs were that this length could be different between different inputs, different sequences, right? We argued that one of the reasons for inventing RNNs themselves is because these sequences could be of different lengths, right? But we are now completely doing the opposite thing by doing padding, which is literally what are we doing? We're making everything of same length. We're making x1 and x2 and x3, all of them to be of 600 length sequences. Why are we doing it? So let's take a detour and understand why pad. Okay. So imagine if I have an LSTM network like this, where I have xi1 here, right? And I have my yi1 hat, right? This is my simple LSTM, xi2 and yi2 hat, and xi3 and yi3 hat, right? And xi4, right? And yi4 hat, and so on and so forth, right? So in this, let's take our inputs, right? Let's assume I have two inputs, okay, x1, which is without padding. Let's take the case without padding. x11, x12, x13, so on, x1 189, right? Then I have x2 equals to x21, x22, so on and so forth, x2 200. Then I have x3 equals to x31, x32, so on and so forth, x3 150. So there is no padding. So there is no padding now. Now when there is no padding, right, there is of course zeros here. When there is no padding, with the simple, again, this is my time axis, let's not forget that. right? When there is no padding, what is the sequence of inputs that we'll do? First, we will send x11. First, we'll send x11. Then we will send x12. Then we'll send x13, right? Because that's a sequence, right? First, we'll send x11. Then we go in the time axis. Then x12, then x13, so on and so forth. X1 189. And once we are done with this, so once we are done with all of them, next I'll send x21, x22, so on and so forth, x2 200. Once I'm done with this, then I send x31, x32, so on and so forth, x3 to x3 150. Now, if you think about it, when I send each of these individual words, what am I literally doing here? And imagine I have to first send all these 189 words, and then this 200 words, then 150 words, and I have to backpropagate for each of them. I have to backpropagate over time, right? Let's not forget that. So what am I doing here? Literally, I'm doing an SGD-like operation with batch size of 1. With batch size of 1. Because at any point of time, I'm only processing one sequence. I'm not combining sequences and processing them. Because remember, each sequence is a data point. So this is literally like performing an SGD with batch size 1. And this is just too slow. You can do this. You can do this. Nothing is stopping you from doing it. But it will just be too slow. It will take you like lots and lots and lots of time to finish this whole thing. So the alternative idea is, look at this. When you have SGD, if SGD with batch size equals to 1 is small, what do? We perform SGD with batch size equals to K. With batch size equal to K. Let's assume I'm trying to perform an SGD with batch size equals to 5. Let's just say. Right? Then how does my network look like? Right? My network will look like this. I have my network here. Okay. I'll just write the inputs and outputs in a second. Okay. When I try to do a batch size of 5, what will I input here? What will I input here? I will input x11, the first words, because this is the time axis. Let's not forget that. What will I input here? I'll input the first word in my first sequence. I can also input the second word the first word in my second sequence, x31, my first word in third sequence, my first word in fourth sequence, my first word in fifth sequence. Because this input should always take only the first word, right? Look at this. So now instead of, see, this x11 will always go here. Your x21 also will go here. But instead of going like this, first finishing all of them, then finishing all of them, then finishing all of them, instead of doing this, I can batch things. I can take all the first words and send them and create a set here, right? Create literally a matrix of all these first words and send them as one batch. Similarly, I can create a second, see, remember, the second word should go here. So x12, x22, x32, x42, and x52 can go simultaneously through this layer once, right? Similarly, here I can have my third word. But for me to continue here, there's a catch. There's a catch. For me to continue here, each of my sequences x1, x2, to perform batch updates with some batch size, right? I need each of my sequences to be of same length. Otherwise, I can't batch them like this, right? Right? If I say that I want, like in this case, right? I'm saying I want each of my reviews to be of the length 600. Right? So what will I do here now? I will have 600. I will have a 600 time step, so on and so forth. Okay, I'll have a time step here. Let me just erase this time here. So this will input x1 600, x2 600, x3 600, x4 600, and x5 600. Right? If x1, x2, x3, x4, x5 were not padded, if they were not padded, I wouldn't have been able to batch them together. And if I don't batch them, it's just too slow. So this padding operation is done primarily to allow a batch update with some batch size. And this will speed up. This will speed up your training in LSTMs. Right? This is a very, very important thing. Creating padding, especially for text sequences. Especially for text sequences, you'll see a lot of these padding operations. They're primarily meant for batch updates. It's a very, very important part. And a lot of people don't get this full details. Like I've seen a lot of interviews where people cannot explain this batch update and why we're doing padding very clearly. And it took me, frankly speaking, even for myself, when I learned this first time, it took me a while to get a hang of it, right? So now let's build the model. Very, very simple. Let's go here. Let's build the model here. Okay, my model is this. Okay, I'm creating a variable called embedding vector length of size 32. Right, I'm creating a variable called embedding vector length. It's a sequential model, and the first layer that I'm adding is called an embedding layer. Now you might wonder what is an embedding layer. So let's go to the documentation. If you just type embedding layer KRS, you'll get this nice documentation. What an embedding layer does is it takes indices like this and returns vectors for you. So it takes indices like this and it returns vectors for you. And embedding layers are used a lot. They're used a lot in your they're used a lot in your NLP tasks, right? So the way this architecture looks, so let me just start a new page here. The way this architecture looks is this. First, I have an embedding layer. And this embedding layer, remember, see, each of my words, so I'm taking only 5,000 words, right? I'm taking a maximum of 5,000 words. Each of my words can be represented as a 5,000 vector one-hot encoded vectors. It's a one-hot encoded vector of size 5,000. So I can represent each of my words like that. So this embedding layer, you can think of it intuitively like a word-to-vec, because word-to-vec is one example of an embedding. And what does the embedding do? This embedding layer, if you give it an input, let's say if I give an input of word 5, it returns me a vector. Okay, that's what it does, right? If I give it, let's say word 1, it will give me a vector representation of this word. Now you might wonder, why are we doing all of this embedding layer? Why can't I just simply use the word-to-vec for this? The reason being, this embedding layer can be trained as part of your task. See, if I used a word-to-vec, for every word there is a static word-to-vec. I'm not learning it as part of my task. Okay, so let's construct it. Just be a little patient. I'll explain all of these details. Okay, so this embedding layer, literally, this embedding layer that I have, right? This embedding layer. So I have my input here. I have an embedding layer, and the embedding layer. If you see this documentation, I'm saying create an embedding layer with the input being the number of top words. I have 5,000 top words, right? And I want the output to be of size 32. I want this to be of size 32. So how many parameters do I have here between my input and embed? So my input can be a 5,000 dimensional vector representing each word, and my output is size 32, which means I have 32 activation units here, right? So the number of parameters that I have between my input and embed layer is 160K. So when I finally print model.summary, it actually tells me how many parameters are there in each layer. And I strongly recommend you understand how these number of parameters were derived, right? Remember, each of my word is represented, I have a maximum of 5,000 words, right? So I can represent each of my word with a 5,000 dimensional one-hot encoded vectors. This is my number of words. This is my output size, my output vector size. My output vector size is 32. So I'm literally creating a 32 dimensional vector output by taking the input and applying this embedding layer, first layer, right? And it has 160K parameters. It's important, which is nothing but 5,000 multiplied by 32. Simple, straightforward there. Because I have 5,000 cross and I have 32 activation units. Because if I want a vector output of size 32, I need 32 activations, right? So that's what your embedding layer looks like. Okay. Next, go to the next layer. Let's go to the code. So first I have done my embedding layer. Then I have an LSTM 100. What does LSTM 100 mean? LSTM 100 literally means that I have 100 LSTMs. This is my first LSTM, right? I'll represent an LSTM with this arrow mark. I have a second LSTM. I have a third LSTM. So on and so forth, I have 100 LSTMs. Okay, this is my LSTM 1, this is my LSTM 2, LSTM 3, so on and so forth. So this is my LSTM 100, which means I have 100 LSTMs, and each of these 100 LSTMs takes these 32 dimensional vectors. So this 32 dimensional vector goes to each of these each of these LSTMs. And each of these LSTMs generates an output for me. Each of these LSTMs generate an output for me. So literally I have 100 units parallelly. Think of it this way. I have 100 LSTM cells, one behind the other, if you want to think about it geometrically. Right? Each of these cells, remember, each of these cells, this is the input. This 32-dimensional vector is the input. It generates an output. Okay, let me not write it as yi. It generates an output, and it has the feedback loop, because you're going to send first word, then second word, then third word, then fourth word, so on and so forth, right? So this is what an LSTM 100 means, right? So with that, let's understand how many parameters are there in this layer. As I told you, understanding this number of parameters will give you a lot of clarity. Okay, look at this. So there is a very nice blog here that I've referenced here. It's not a blog, it's basically a question answers on Stack Exchange, which explains how many activation units are there in an LSTM layer. And the formula is this, right? If you have an LSTM layer, remember, let's look at this whole thing as one layer, right? Let's look at this whole thing as one layer. How many inputs does it have? It has 32 inputs, right? It has 32 inputs. It has 32 inputs. And it has 100 outputs, because I have 100 LSTMs, right? Each of them is just going to send me one scalar value. So this output vector that I get here is of size 100, right? This is of size 100. Okay, let me just erase this so that you don't get confused with the structure again, right? So I have output 1 from the first LSTM, from the second LSTM, third LSTM, so on and so forth. So I have 100 outputs, right? And the core concept is this: the number of parameters in an LSTM layer with 32 inputs and 100 outputs, right? Or in other words, if this is M, if I have M inputs and N outputs, the number of parameters is 4 times Nm plus N square plus N. Again, remember, this plus N occurs only if you have biases. You have weights, right? For every weight, there is a corresponding bias. And LSTMs in Keras LSTMs by default have biases. If you don't have bias terms, remember, what is your bias term? W transpose X plus B. This is your bias term, right? If you have bias term, you'll have plus N, or else you'll just have 4 times Nm plus N square. And by default, LSTM Keras has biases, right? So let's just insert these values into the formula. The exact derivation of this formula is actually not very hard. I recommend you spend some time and read this question answer section, where it's clearly explained how to derive this 4 into Nm plus N square plus N. Okay, so let's insert it. So N into M is 3200 plus N square, which is 10,000, right? Plus N is 100. So when I multiply all of this, I get my 53,200 here. And that's what you see here. So understanding the number of parameters is very, very important. It gives you a lot of clarity, because I learned about this formula and its derivation only when I asked, why does this have 53,200 parameters? Okay, so that's why whenever you train a network, try to understand these number of parameters. And once you understand it, you get a lot more clarity, right? Now let's look at the next layer that I have. So I have my embedding layer. I have my LSTM. Then I'm connecting it to a dense output. So I'm connecting a dense to just one unit, one activation unit, and it's a sigmoid activation unit. So what am I doing here? I'm taking all these outputs and I'm connecting it to a single sigmoid, which will generate my yi hat. Remember, my yi hat is basically binary. My yi hat is binary. So I'm taking all these 100 inputs here and one bias term, right? And what is this? This is nothing but sigma of W transpose X plus B. This is your simple sigmoid function. And how many weights are here? You have 100 weights. You have 100 weights corresponding to each of these inputs, and you have one bias term. So you have 101 parameters here, right? So if you sum up all of them, you'll get 213,000 parameters. And then I'm just saying my loss is binary cross entropy, and my optimizer is Adam, and I also want to report accuracy. Very, very simple. Nothing very fancy here. Then I printed the model.summary so that I get the idea of what the model looks like, right? Last step would be simple. You just say train or fit. In this case, model.fit, you just model.fit, and here we are using a batch size of 64 and we are using 10 epochs, right? And I'm going to evaluate the model on my test data at the end, and I'm going to print its accuracy. So this code, as you see, is still running, right? So at every step, look at the training error, right? The first training error was 78%, right? My training accuracy was 78% at the end of first epoch. At the end of second epoch, I have an accuracy of 83%. Third epoch, something went wrong. But eventually, by the time I come to sixth epoch, I have 90% error. By the time I come to seventh epoch, I'm already at 92.65% accuracy. And if you just run it for 10 epochs, I think you'll get a very good accuracy of over 90%, right? Very, very straightforward code. So the most important takeaway in this video, the most important takeaway for you would be using padding. Why we need to use padding? Look at this. Padding is a very important lesson here, and how batch LSTMs actually work. That's the first key lesson. The second key lesson is the embedding layer, and most importantly, this whole architecture, right? What does LSTM 100 mean? It means we have 100 LSTM cells, and each LSTM cell might learn a different thing about the data, right? So in reality, we never just have one LSTM cell, right? And look at this. Each of these diagrams here that we have, each of these is equivalent to your whole this, right? When you unwrap this, because I have the loop here, when you unwrap it over time, when you have one word followed by the other word, each of them, so each of these here is equivalent to one time unwrap of the RNN or LSTM here. So each of them, so here you have 100 LSTMs, and each of them can be unwrapped over time again. That's important to understand. That's why I've drawn this very carefully with just a loop. So whenever you see this diagram, this internally means that you have a time axis here and you have a time unwrapping, right? From one step to other step. So, and after that, it's all straightforward then, very, very simple code, and the model accuracy is very good. So I'll provide reference links to all of these things. So you have some of the reference links readily available in this IPython notebook itself. We will share this IPython notebook in the description section of this video.